יהיה שם, הפתעה.
לפחות יש לי לידי טוב למה לא בא לסמינרים עכשיו כאן.
אוקיי, נתחיל?
כן, sure.
Okay, let's get started. Thanks everyone for coming, and thanks Chaim for being present here and being very flexible with the time.
Sure, yeah, thank you for coming. So I mentioned, usually I'm the one who walks in 2 minutes late, so if anyone who walked in like after I started, so I'm totally, I forgive anyone. But yeah, so I'll be discussing a paper that I've been working on the past, I guess, year or so that's currently under review, together with Dorita, Prof, and Rohit, and on the large-scale drivers, heat waves in the Eastern Mediterranean. So I have the fortune. I have the privilege to only have one paper to be presenting, so there's lots of time for questions. So yeah, so please stop me as I go through this. Yeah, so why do we care about heat waves? And part of why we care is that it has substantial health impacts and impacts on utilities and energy and transportation. And these heat waves are projected to become more frequent over the coming century. This is just one example, one way of visualizing this increase in the frequency of heat wave. This is just showing a change. The left column here is a change in the number of days, the temperature exceeding 35 degrees Celsius, in a 1.5 degree warm world, 2 degree warm world, 3 degree, and 4 degree warm world. And this is sort of 35 degree threshold is sort of somewhat arbitrary, but it gives you a sense of sort of extreme temperatures. And you see an enlargement of the regions of the world, and also and does go 0 to 200 days per year. And you see a sort of a broadening in the area of the world, and also the number of days where you have these extreme temperatures in a one climate. And the right column is the change in the number of days from a historical reference period for 1.5 degree, 2 degree, 3 and 4 degree warm world. And we see, basically essentially nowhere where there's a reduction in the number of extreme heat days, but lots of regions where there's an expansion in the number of extreme heat days. And so this is something that's robustly predicted by models, and it sort of makes sense that if you have a warm climate, then the details will also warm as well. What's interesting is that how much do we trust these models, and are the models capturing heat waves for the right reasons or not? And so what I'll be, that's in this work, in this paper, we focus mainly on the historical period, but eventually we're going to be looking at models as well as part of this project. And it turns out that models have some issues with heat waves. Just here's one paper that I'm just picking on for at least in some sectors, models have problems with heat waves. This is a paper that came out, I guess, a couple months ago, focusing really on Europe, but we're on the map here at least, so it's like this paper then. Basically, the conclusion of this paper is that models underestimate heat wave trends in Europe, and so the way the evidence they provide to demonstrate this claim is they look at 273 individual CMEP6 runs over this period here, 2052 to 2022. And for every single one of those 273 CMEP runs, they calculate the trend in daily maximum temperature and also daily average temperature, if I understand correctly. And they then, so mean temperature, and then they just what fraction of this 273 individual CMEP6 trends exceeded the corresponding trend in Area 5 data. So maybe you take basically the trend of daily max temperature in Area 5, you take the trend of daily max temperatures from each of these models, and you then ask the question, where does Area 5 fall in the PDF of the 273 models? And what they find is that in this region here over France and northern Germany and into the UK, the models basically systematically underestimate the frequency, this enhancement, this increase in the number of extreme heat events. And it's interesting to know over us, actually, the models are actually pretty good. It appears the models seem to be capturing a pretty good job at the trend, at least over these 72 years, and heat over us. And if you look at the mean temperature, there's still an underestimate, but it's within the range more so. And if anything, the models are actually signaling a slightly warmer trend than has occurred.
Yeah, I have a question. It seems like localized over land, just ocean is actually overestimating. So it seems to indicate that it might be for local reasons.
That's certainly,
use or something like that. So the question is, to what extent is it local or global synoptic circulation?
So this paper then argues, actually this paper, there's another paper, Patterson et al. Also from last year, or 2 years ago, where they argue that the models are, I mean, this is a more general question, that we have this sort of wave 5 trend in atmospheric circulation in summertime over the past several decades, and models appear to be underestimating it. It would indicate that it seems to be a dynamic issue, and this paper also goes into that. They try to argue it's the dynamics that are wrong or underestimated by the models, but the thermodynamic part is actually okay. I think it is the dynamics, not the thermodynamics, but I think it's an area of active research.
So it's global circulation issue.
Yeah, circulation issue.
Maybe not global.
The wave 5 pattern you see over the entire northern hemisphere. So in global, I mean hemispheric. So depending on where you are, I mean, in the North Atlantic it looks like this, but if you actually did like a global view, you would see you'd see regions of red and blue, and in others you would see more regions of red and blue and less of white than you would otherwise expect if it was just randomly distributed. But I guess they don't actually have the plot, so I can't promise. But I think my understanding is that that's what you'd see. That there'd be many more regions of red and blue than you would otherwise expect because of dynamics.
So just to clarify what you mean by heat extremes, so these are daily or
these are daily max
waves or
so this is just daily max. They're not actually looking at waves per se. They're just taking daily max temperatures and a trend in that, and they actually normalize it by the global mean temperature as well. So in other words, some models, so there's a widespread, and so in other words, for each model they normalize the temperatures locally to be so that the global mean temperature. In other words, there's another discrepancy between the models and observations is just the total global mean temperature. So they basically they actually do both. They both normalize it and don't normalize it by the global mean temperature, and they say you get the same result either way. I'm going to talk about this panel in a second, but for this panel, they do normalize it by the global mean temperature, just to account for the fact that some models have a bigger rate of warming than other models. This particular discrepancy is the argument at least is robust with whether you normalize or don't normalize.
Normalize to the global temperature on the day.
No, of the trend. This is all based on trend. So in other words, some models have a stronger warming trend than other models. So if you have a bigger warming trend, then you expect there to be more warming in any given region as well. So they actually normalize the regional trends by the global trend.
So you detrend.
You detrend, yeah, basically. Well, you're not detrending it. You're normalizing. Like in other words, if your model has a 1 degree per one Kelvin per decade versus or I don't know. That's
Essentially.
basically. So just to talk about this now. So this is just showing each of these 273 runs. Each one of these dots here, there should be 273 dots here, and these are a whole bunch of models. And so this is just the trend in this box here. For each one of these dots is one model. This is the analysis trend. So it's about 3 degrees. So this is the trend in. Well, you probably can't see this very much, but yeah, this is basically 3 degrees warming in this region for every degree of globally average warming. And the point of this is that these dots are all systematically on the left side of this vertical line. And the models, doesn't matter which one we look at, pretty much all the models are underestimating the warming in this box here.
If you force the model with the SST pattern, the observed SST pattern, would you get better result? Is it the
I mean, I don't know. Good question. I don't know. That's how the
I know that models have, they have a hard time to capture the North Atlantic warming or the location and intensity of it.
So that would Related to that, yeah. So I don't know if that's related or not.
Yeah, that is actually a manifestation of missing the warming hole.
Yeah, it is, yeah. So anyway, so it implies that at least in some parts of the world, there are indications that models are missing part of the trends, and maybe that sort of motivates our digging deeper into understanding heat waves and understanding what are the drivers of heat waves and whether models can reproduce the drivers of heat waves. And so for this work, we're focusing on our region specifically, but I have a couple more slides that are more general. So if you want to understand what the models are doing fit for the task and able to resolve heat waves or heat extremes, then we need to understand the processes that lead to heat extremes. And so this is a schematic from this paper here, looking at all the various kinds of processes that can drive heat extremes and how they may change in a future climate. So we'll start off with the dynamics part, because that's what I like. So you can think of a velocity wave train, some sort of velocity wave, and associated with this velocity wave, you have a region of a ridge and some blocking, perhaps, and subsidence, and that can give you stronger, more frequent heat waves in this region here. You can also think of this velocity wave train inducing convection of warm air and warm advection, and that can help induce a heat wave. And I'll actually talk about this going forward. There's talk quite a lot about warm air advection. You can also think about sort of a region with moisture and attending airstream that helps induce the block. There's also local processes involving soil moisture and sensible heat fluxes. If you have a drying at the surface, then it will have more sensible heat fluxes and less latent heat fluxes. And that could also, you can also have changes in cloud cover, which can also affect incoming short wave radiation. That will affect heat waves as well. Stratification changes as well, which we expect in the future climate, will affect the warming from a given amount of substance. That will, the amount of warming you'll get from a given substance depends on the stratification. So this also matters. So this is just a sort of a laundry list of processes that matter, both in the future climate and also the present climate. And I'll be focusing in our region, specifically on the sort of warm air advection and the subsidence and some dieback processes as well. But there's a lot. There's quite a lot of processes involved, and in any given region, the processes that are important may be different or can change. And this is another sort of schematic. Okay, so what are the sources of predictability for heat extremes? And really, part of my motivation was understanding how far in advance are heat waves predictable in our region specifically. And in more generic sense, looking broadly, more globally, there's a whole range of processes that can be used to predict heat waves, heat extremes, from sensible heat flux from the surface, and dieback processes and descent and anticyclones and blocks, velocity wave packets on slightly longer time scales, sort of velocity waves propagating from one region and helping induce a block, or maybe if you can predict that, that can give you predictability up to a week or two. And then more generally, that if you have a season with less rainfall, soil moisture deficit, and that helps induce sensible heat fluxes and reduces latent heat fluxes, that will help give you higher temperatures. Remote forcing from EMSA, IOD, MJO, which in turn is related to these velocity waves. These can help induce velocity waves that propagate away from a region and affect surface temperatures and SSTs as well, and then finally greenhouse gases. And I'll be sort of focusing on, I'll be talking about the monsoon shortly, and the effect of the South Asian monsoon and summer temperatures in our region, and the velocity wave that's associated with these monsoons. So the main questions of this particular work is focusing on our region, how far in advance are heat waves predictable, and what are the other precursors on large scales that help set up the conditions for such a heat wave. Those are the two main questions of this paper. And there's been some previous work on this topic, focusing on the role of the South Asian monsoon, perhaps a low from the west that helps impact temperatures, warm temperatures from the south and the Sahara or further south. Perhaps is there some indication that maybe the Sahel is involved, if you have a stronger monsoon in the Sahel. Is there relative sea surface temperatures as well? So these are all the various things we're going to be looking at. And then also, what are the relevant importance of subsidence versus normal temperature reduction versus diabatic heating? So these are various questions that I'll try to answer over the next half hour.
Surface temperature you expect to affect the predictability of time scales of weeks?
Yeah, I mean, I'll show that, yeah. If you have sea surface temperature anomalies in the western, I'll show shortly, hopefully, is that if you have sea surface temperatures anomalies in the western Mediterranean, yeah, or even the eastern Atlantic, northeastern Atlantic, that could help.
Not eastern
Yeah, not local, yeah. I mean, so when you have concurrent with the heat wave, you have warm temperatures in our region, warm sea surface temperatures in our region, but if you go back, let's say 10 days, you'll see sea surface temperature anomalies elsewhere. Yeah, and so eventually we want to look at models as well. That's because Andre's here. So, but yeah, eventually we want to understand whether models capture the large-scale drivers of heat waves in our region and in the historical climate, and also for future projections. And we're looking in this particular talk at observations only. And so just. So I'll be switching gears to really thinking about our region, and so just starting off at the very beginning, the large-scale precipitation, the omega, 500 megapascals in our region in summertime. We have this large region here of rising motion and of course our subsidence over us, and this helps set up the large-scale circulation in our region in summertime in the climatology. And what matters, and associated with this rising motion and subsidence is what's known as a South Asian monsoon anticyclone. So at upper levels here, and here I'm looking at in this case 350 Kelvin, so upper levels, really near tropopause, or actually above that, just sometimes. You have this enormous ridge that's there pretty much the whole summer. It's fed by this diabatic heating, and it extends all the way from essentially the entire zonal extent of Eurasia. And associated with this monsoon anticyclone, there's anomalous subsidence in our region, and rising motion to the east. And so this is sort of fed and helps feed back on, fed by the convection, but then it helps feed back on the convection and helps induce the subsidence over us. And so if you actually look at rising motion and here, this is like a cross section. So now this is South Asia over here. This is the Tibetan Plateau, and we're over here somewhere. So there's this rising motion here. This is again omega velocity. We have rising motion here over South Asia, and we have subsidence over Eastern Mediterranean into our region also. And so this is what
topographic force.
It's forced by. Yeah, so the substance over our region is a balanced response to this anticyclone. So in other words, so the topography modifies the specific location. So that if you look at the specific regions in which you have substance is sensitive to topography, but the general sort of rising motion here in substance over us is sort of a balanced response to the Rossby wave that's induced by the huge amount of diabatic heating in the South and East Asia that happens in summer.
The cyclone is over Tibetan Plateau, but it is supported by the Indian.
Yeah. So in terms of actual diabatic heating and upper level diabatic heating, it's what matters is it's not just the latent heat, it's the full range of diabatic processes that give you. So this is for focusing on the diabatic processes, but I'm looking at in this case pressure on an isotope. So so it moves it further to the north. So associated with that, so your atomic level of precipitation is not necessarily all that far north, but the upper level diabatic generation of this ridge is indeed a little bit further at upper levels, is a little bit further north, and you end up with this precip here and lack of precipitation over us. and then that. And this is all in the climatology, and I'll be discussing shortly the anomalies, like the deviations from this time mean, and how deviations in the time mean from this monsoon and subsidence affect temperatures over us. But before I go there, just one last sort of intro slide before I show the results. Models don't do a very good job. This is CMIP 5. I don't know if someone is on. I guess Andrew will look at CMIP 6 at some point, but yeah, eventually, this is a plot that was from based on CMIP 5 models. The black line is a climatological omega, so over in this latitude band. So this is South Asia here. You have anomalous rising motion here. You have anomalous subsidence over us here at 30 degrees. And you have a whole bunch of different CMIP 5 models in this case. And the point is that the magnitude, so all models get this in a sort of qualitative sense, the rising motion over South Asia and the subsidence over us, but the magnitude is not very consistent. So just the basic sense that, errors on the order of 30%, 40%. You see those kinds of like deviations. Maybe not 40%, but certainly 30%, 40%. You have deviations in the magnitude of the subsidence in our region here, which is sort of. This is a CMIP 5. It could be CMIP 6 is better. I guess we'll find out. But that's something that's interesting to know. So now I'll sort of switching gears and really getting to our results. We're so interested in how far in advance heat waves are predictable, and what are the precursors on large scales that help set up a heat wave in our region here. And I'm really interested in all these various processes, particularly the Asian monsoon, those from the west, sea surface temperatures, and then focusing on temperature budget to understand specifically, like Eulerian temperature budget, what's going on. So I'll be showing a lot of panels will look at this. These are beginning of my results. So it's just a climatological height, 1,000 pascals. And in summertime, we have our monsoonal trough, near surface monsoonal trough, and then there's an extension to that. The Persian trough, known as the Persian trough, extends into Iraq and into our region here. There's a little tongue here into the Mediterranean. We have anomalously warm temperatures in the Indian Ocean and warmer temperatures in the Mediterranean than you do over the Atlantic. And you also have, of course, your rising motion here, your substance here. And we also, I'll be focusing on anomalies from this mean state. This is the mean state, and I'll be focusing on, we're showing anomalies from this high mean state shortly. This is the OLR, background lava radiation. We have our convection here and also here in midsummer, in contrast, clear sky conditions in this region here, and I'll be showing anomalies during heat waves shortly, and then diabatic heating from 400 hectopascal to 700 hectopascal. You have, of course, your substantial diabatic heating in this region here, and also here in Sahel, and clear sky cooling over us, and finally divergence here and over here, and also convergence here. And so we're interested in how these things change, and before we see how they change, let's first define heat waves. So the way of defining a heat wave in our region is I'm using what's known as EOBS data. So EOBS is basically a project in Europe where they collected station data and they generated a gridded temperature data set at a 10th of degree resolution, so 10th degree latitude and longitude, which is actually very helpful for those people who don't like dealing with station data. And with me, it's actually very nice to have someone do the interpolation and the gridding for you. So these are each of these axes here is a station that is fed that EOBS uses. So there's I think 27 stations total spread out over Israel, and this data is fed into the EOBS algorithm, and they generate these gridded data sets over our region and also over basically all of Europe. And lucky for us, we're close enough to be incorporated. And what I've then done is I take the gridded data set and I average the gridded temperature in 6 different little polygons here. So this is like a negative sector. Here there's a Dead Sea sector. There's a Galileo here. There's a coast over here. There's a mountain sector here. And so I average the temperature in each of these polygons here, and both for Tmax and also Tmin, so the daily average temperature and also the daily maximum temperature, and generate a ontology of those two, and then look at the 95% threshold, and of that, and then the ontology for each day, and then a PDF. And if the temperature exceeds the 95% threshold for 3 consecutive days, then we call that a heat wave. This is sort of a standard definition. Pretty typical. And then we've also done 90%, and it's basically the same. We've done 90 or 95% for 3 days. This is a sort of typical way of defining these events. And we're looking in May through September only. And so you end up, after you do this, you end up with a list of events. So this is, in this case, daily average temperature. Here I'm showing just sort of a snapshot, or just a little snippet of the table. There's a table that goes on and on. But these are just a list of events. For example, this is one of the events in the coast that started in August 7th, 1998. This particular event occurred both in the coast and also the Dead Sea, and also the negative, and also if you do the average over all of Israel. So it turns out many of the events are common. It turns out not to actually matter which particular region you look at. Most of the events and most of the composites I'll show are the same in all regions. And there's, so then there's also the duration of the event and the maximum temperature. And so you can generate a list of events like this, and then look at how the anomalies look like with respect to this climatology going back before the event starts. So for each of these 6 fields, we're going to look at anomalies of these 6 fields relative to the onset dates. So for example, for the coast we have, let's say, 20 events. For those 20 events, we have an onset date, and then we look backwards in time from the onset date and see what the anomalies look like for each of these fields. So let's jump into results. So this is the geopotential height at 1,000 hectopascals. I'll start on the far right here. This is the day after onset, the 3rd day after the onset, minus 2 days before onset to the onset date, 6 days before to 3 days before, and 10 days before to 7 days before the onset. And there's 21, this is for the 21 heat wave events that found over the mountain for the 95% threshold for daily mean temperature. And what you may see here is a weakened Persian trough. So in the climatology, there's a Persian trough in this region here. And when you have a heat wave, the Persian trough is weakened, and you also have this little low that's centered here over Egypt. So that's the contours are the Z1000. The solid lines are the actual temperature anomaly itself. The temperature, in this case, 850 hectopascal temperature anomaly on days 1 to 3. And so as you expect, there's heat waves, so there's anomalous warmth at 850 over here, and this Persian trough, and a ridge, anomalous ridge here, and a trough here. So you have this low affecting warm temperatures and also the weakening of the Persian trough. If you go backwards in time, you see weakening Persian trough as well 2 days before the onset date, and you also have this low. And if you go, let's say, 10 to 7 days before, there's not much going on over the Persian trough, and you get this little bit of weakening already here, but it's relatively small, much smaller than you get later on. You have the beginning of this low that's propagating to the east, but at this point it's not really strong. So you have weaker Persian trough and low from the west, but it's not clear. These are not things that are necessarily predictable. So let's move on to the next field. The next field is sea surface temperatures. On the onset date itself, you have almost really warm sea surface temperatures over our region here, and also over. I should mention these SSTs are detrended, so we were focusing on only the sub-seasonal or like the variability SSTs that's beyond the trend. And so yes, you have anomalously warm SSTs that are here and also over here. And as you go back in time, the warm SST plot moves to the west and is really focused in the western Mediterranean, 10 to 7 days before the heat wave onset. And you also, what's interesting to note is that there's not a heat wave per se, but there's anomalous warmth, and also both in the sea surface and also at 850 hectopascals, 10 to 7 days before in Western Europe.
So this is the length there, the leftmost panel in the second row is about what? A fraction of
It's about half a degree or so. Yeah, half a degree. I mean, locally up to half a degree. Yeah. And then as it gets closer to us, it reaches a degree.
Right.
So now I'm just adding in some more forms. So omega 500, OLR, and diamagnetic, which all sort of tell you the same story. I'll start here. So this is omega 500. 7 to 10 days before the onset, you have a weakening of the monsoon, on the substance of India. And then as you get closer, you also see associated with this low, that's over here you have rising motion here, what's important for our is already 10 to 7 days before the onset of the month on the heat wave over us, you have a weakening of the monsoon, this region here. And you see that not only in omega, but also in OLR. There's anomalous, the fewer high clouds, and also in diabatic, the diabatic is anomalously weak. What's interesting is that over the Sahel, there's not much going on. So there's basically no signal in the Sahel. So it's really just the monsoon that seems to be what matters. And it's also interesting is that even if you look at, let's say, on the onset data just before, the subsidence isn't really over us. So there is anomalous subsidence, but it's really further north. So in other words, it's not so much, I'll talk about the diabatic temperature budget later, but it's not so much that there's a direct warming from subsidence over Israel, but rather the subsidence that occurs is occurring over Iraq, Eastern Turkey, Kurdistan, Turkey, Iraq, not so much over us.
So I can add some support for that. During heat waves in summer in Israel, you can see the tropical convection to the southeast in Arabia and further to the Garfinkel. The outflow cirrus comes around in southeasterly flow and subside here.
Over us or interesting.
So you see the high clouds got up there and subside here, mostly.
So I guess the point of this is that so there is substance for the substance. There is substance, but I guess the substance maxes for the most of this panel is further to the north and further to the east. And if anything, there's actually anomalous rising motion over Cyprus. Which is actually interesting. Chronologically, you have substance here, and that substance, if anything, is actually weakened during a heat wave. So it doesn't seem to be like the. At least, So it's
after the West helps.
The West, So just a summary so far. So we see in the lead up to heat waves, you have a weakened push and trough. There's a low from the west. Sea surface temperatures are anomalously warm in the western and central Mediterranean, and there's a weakening of the Indian monsoon. So the next step is to try to actually predict heat waves. Basically, we've identified at least two processes that we think can be useful for predictability. The first is warm western Mediterranean sea surface temperatures. The second is a weakened monsoon over South Asia. And we asked the question if we have both of those. So ignoring heat waves for a second, just putting heat waves aside. If we have a day in which there's a weakened monsoon and also warm SSTs in the central and western Mediterranean, if you have both of these together, does that lead to predictability for a heat wave or for anomalous warmth over us? And so what we've done is we've formed composites of days or composites of events which have simultaneously a warm western Mediterranean and a weakened monsoon. There's 37 such days in summer that we've identified, and also a composite with simultaneous cold western Mediterranean and a strong monsoon, and then take the difference between these two composites in temperature over the coast, this polygon here, in the mountains, this polygon here, and the density, which is over here. And it turns out that if you look just before the onset of these events, there's not much going on. Temperatures are relatively climatological, but then if you look 10 days to 30 days later, you have this warming, this diabatic degree, which corresponds to around half a standard deviation. So you have a relatively strong warming in these two regions, and also the other two regions as well. Like here's some warm regions, and up, in the Galileo, almost 1.5 degrees of warming. when you have, if you know that there's going to be a warm Mediterranean in week monsoon, you can sort of, in some sense, predict anomalous warming in our region over the following month, which gives it some subseasonal predictability. So predictability of anomalously warm conditions on subseasonal timescales based on the SSTs in the South Asian monsoon. And I should emphasize that this predictability is not deterministic, so it's not like there's a one-to-one correspondence between these conditions and temperature over us. Any predictability will be deterministic, will be probabilistic, not deterministic. So just to emphasize that what I'm showing here is for these 37 days with the warm Mediterranean and wet weak monsoon in red, and the blue is the cold Mediterranean and strong monsoon. These are PDFs of temperature, and this is actually the olive region, I think. And the PDF of temperature anomalies in days 10 to 30. And so the red PDF is certainly shifted to the right and the left. The blue PDF is certainly to the left, but there certainly is a lot of overlap, and you can't say unambiguously that there will be heat wave if you have this. So the next step of the last part of this talk is the role of temperature convection versus subsidence versus diabatic heating. Which of these three processes matters most for these heat waves? And the way we're going to address that is by taking the temperature equation, thermodynamic equation, and trying to close it in using the analysis data, which is always maybe a bad idea to try to close the budget using data, but we did it. We tried anyways. So you have your temperature tendency, temperature changes and deviations in temperature. It can be due to horizontal temperature advection. This vertical term, which includes both the vertical advection and also the adiabatic expansion and compression. Here's our diabatic term, and this is a residual, which is certainly not going to be small on local by grid point, but maybe broad scales the residual will be small. And so what I'm showing here is just get a sense of the residual. This is the action temperature tendency on the top. This is the sum of these three terms. And so if this looks like this, then the residual is small. And this is 6 to 3 days before. This is 0 to 2 days before the onset of these heat waves. So where this looks like this, then the residual is small. And I think if you squint and you don't look at the fine details, it's not so bad. If you look at the fine details, it's not very good at all. But we're using the analysis data. So what can I tell you? So hopefully you're convinced that this is not that this is useful.
Do you multiply it by 2?
Yeah, so there's a factor of 2 because of the delta. So there's a factor of 2 that we spend a lot of time. I spend a lot of time trying to figure out what's going on, which I think has to do with the delta type. I'm still struggling to figure out where exactly the delta. There's a factor of 2 there that I think has to do with the temperature, with the time delta. But it was sort of a placeholder for me that I need to figure out. But I've already spent hours trying to figure out. But yeah, there's a factor of 2 that I'm sort of from the time stepping. At least in a general sense, I think it's hopefully useful to do this.
This is temperature at the surface?
This is 850.
850.
Yeah. So so in analysis, there's also an analysis tendency, and so this is basically ERI5. ERI5 doesn't give you the analysis tendency in a very useful. It's actually almost impossible to get the analysis tendency from the model. The way they do 40 bar, the analysis tendency is hidden essentially. I mean, I guess the downside of doing 40 bar is that you don't really know what your analysis tendency actually is. It's sort of you have to go back into the forecast run and output it like time step by time step, and which they don't really make easy for users. So in this case, I don't have the analysis tendency. And there's actually another study where they try to do the temperature budget in ERI5 using model level data at the surface, and they also find residuals. So I think there's an analysis tendency that's not small, and I don't know how to get it easily using ERI5. I don't know. At least for our purposes, the argument is that this sort of looks like this sort of looks like this, so we can then take this and decompose it into the vertical term, horizontal term, and the diabatic term. And these next three panels here, which is the vertical term, the horizontal term, and the diabatic term. And I think what matters is that the horizontal, at least in our region, the horizontal term is the most important. And further north over Iraq, Kurdistan, like northern Iran, the vertical term matters more, but at least in our region, it's really the horizontal term. And if anything, actually the diabatic term is actually a negative feedback. When you have anomalously warm temperatures, you actually have anomalous long wave radiation, enhanced long wave radiation, you actually have a negative feedback from diabatic. So this balance is different in every region. Right? So in other words, it's non-trivial. In our region, it's horizontal, basically everything, but in other parts of the world, the vertical term matters more, and in other parts, the diabatic term actually matters the most. And you can then take the next step of taking this horizontal term, which is this term here, and then decomposing it as follows. So we have a U bar and a T prime and a U prime and a T bar. So the bars are the time mean, the prime is the deviation from the time mean. So this term here, so this term here is the anomalous wind and a time mean temperature. So we can think of this term as like the winds are anomalous. If you think of a weakening Persian trough, and the Asian winds are weaker. So in other words, U prime is opposite. U prime opposite to the combinatorial. U bar and V bar. I say weakening Asian winds, and you have your time mean temperature. So I guess in our the story we're trying to tell, this is the Asian winds weakening. So if you have a weakening Asian, if the winds go with the time mean temperature, you can then sort of decompose. You can then plot this term only. And if you plot this term only, that's what this is here on the bottom here. And this is the weakened Asian wind term. And the point is that this looks like this to a large degree. It's a little bit weaker in magnitude, but the pattern is more or less set up by the fact that the Asian winds are weakened, which is associated with the Persian trough as well. And this is also, not just the Asian winds, but also the low from the west as well. So I think that's basically.
What's the magnitude of the residual compared to the smallest?
Well, the problem with the residual is that it's very patchy. It's very, in other words, especially over Turkey. So if you actually plot the residual over ocean, it's not so bad. If you go over land, it's not very good. And so I guess you would have to do some smooth. You can actually try to quantify it, and if I try to quantify that, I would apply a huge smoothing to these fields, because I wouldn't expect the budget to actually be balanced, like grid point by grid point. The best I would hope for is in a large region that things are balanced. Or the
regions that you do, when you do average it over a certain region, then what do you get?
Yeah, I guess we could do that. I guess we could do that.
Like half of the smallest term that you keep, or
yeah.
10%?
So I haven't done that. I guess if I should be, we'll find out what the reviewers say. That's I guess a good suggestion to like have a box over a big box. Not small, a big box over this big blob, and then average each of these terms in that box, and then residual, and then hopefully the residual is small.
Do you know the largest one? You know which is the largest?
Yeah.
So it's the advection.
Yeah.
So forget about that. You have about 3 candidates for the smallest term.
Yeah. So it's I'm guessing the residual will be bigger than the diabatic term. So I mean, certainly if you look grid point by grid, I haven't made a public residual, and certainly grid point by grid point is very patchy. So if you look at individual points, then this is much less than the residual. There's also an analysis I say.
How would you put it into the residual?
We spent, so Chaim literally spent like weeks trying to download. So also the diabatic heat curve, also you don't get at pressure levels, you get at bottle levels, and then you have to convert it. You get the grid files at bottle levels, you have to then convert to an SE file. He spent literally weeks trying.
How would you put it into the residual?
Well, we spent all the time doing this. We did, yeah. But you're right, yeah. It turned out to be. It's also negative feedback. It's certainly not helping the heat wave. If anything, it's actually damping the heat wave. It's hard to see, but there's blue here. So essentially, enhanced long. We assume it's enhanced long wave emission when you have a heat wave. But yeah, I mean, there's an analysis tendency that we don't really know what it is. So I think that's basically that's the story. So we have heat waves. We want to understand where heat waves come from and whether they'll increase in the future, and trust our models if they're predicting an increase in heat waves in the future. Before we can even look at models, the first step was to look at observations and see whether in observations models understand the processes that lead to heat waves in our regions specifically. In other words, we have this laundry list of processes that are, so we have this laundry list of processes that are important globally, but of all these various processes, what matters in our region? And it turns out in our region, it's mainly the things that are actually predictable are SSTs, sea surface temperatures, and the weekend Indian monsoon. These precursors are evident more than a week before the onset of the heat wave. So we should be able to predict marvelously warm temperatures and periods in our region. And if these are present, then we should be able to predict warmth. The temperature budget indicates that it's mainly horizontal temperature advection, not really subsidence and not really diabatic processes. And
so number one is temperature advection, number two is the subsidence.
Well, in our region, subsidence is really all temperature advection in our region. Subsidence matters more further to the north. So in some sense, it's a little bit. So the subsidence, I think, matters for the Persian trough to begin with. So the Persian trough is weakened. And part of the reason why this Persian trough is weakened, in a balanced sense, the substance is happening over here, and that's exactly what the Persian trough is getting weakened. So, in some sense, it's coupled, but like the substance that's happening in this region here is associated with the weakening of the Persian trough, which then gives us the horizontal temperature advection. So that's I don't think a budget is great, but a budget can't give you the full, not necessarily. Give you the full story at all times. But at least in a sort of temperature budget sense, the most important contributor was horizontal temperature advection, and in particular the term representing the advection of conventional temperatures by the weakening winds. So that's it. Thanks.
I think these results are consistent with previous work that tried to examine the subsidence part is essentially the monsoon desert mechanism. So previous works have looked at that and found that it's weak in Israel. So this is consistent.
So there are some studies looking at So certainly in time so monthly mean and interannual variability. I'm not actually aware of any study that's done this kind of thing on shorter than monthly mean data, which is, there was the original Albert paper from 2004, which looked at one season. But I guess Asaf knows the literature more than I do. But but as you can tell, there was no paper that did this. So.
First few, and I think only two papers looked at that specifically, but I think it's consistent. That's great. But I think it would be interesting as a follow-up to examine not just temperatures, but the wet bulb temperature.
So the problem with the EOBS data, so we actually looked at the EOBS data. EOBS has relative humidity, or humidity, so this EOBS data has, in some sense, so the reason why I didn't do that is because I thought about doing that, and I looked at the EOBS data, and I looked at the time period that had relative humidity over our region, and there was gaps. For this study, I'm using 1982 to 2020, and relative humidity data had gaps. I don't know if it's because the station doesn't record relative humidity, or I don't know what, but at least using this data, we could do that. But I agree. If you care about compound extremes or actual sort of heat index, then you care about humidity also.
I think
so basically with that Lagrangian perspective, it's still consistent with this one.
Yes, I think it's interesting because the advection term is the dominant one. Then the way So advection could also bring moisture, or it could not. So that would, I think it's an interesting aspect that you can add here.
I would like to add to that. I noticed that